Hello everybody, I'm glad you could join me again. In our soil mechanics journey today, we're going to take a look for the first time at a very important topic for geotechnical engineers, and this is the topic of lateral earth pressures. Lateral earth pressures are the pressures that act on the sides of structures or behind retaining walls. We've talked a lot about soil and how soils react to horizontal pressures, so things like geostatic stresses or induced stresses, but now we're going to be talking about the lateral component. There's lots of different roles that lateral stresses in soil play today, and lateral soil stresses are a very good thing. Civil engineers like lateral soil stresses mostly because they provide a lot of resistance. And so if we don't want something to move, we often tether it into the ground. And the soil resistance, the lateral resistance, will keep it from moving. There's different types, though, of say, the way that the soil resistance or the soil loading can play with lateral earth pressures. Take, for instance, this example of where we have a ship that's anchored with the anchor down, buried in the bottom of the ocean, and that anchor is keeping the ship from floating away. You can imagine that as that boat is pulling on that anchor is trying to move this way, but the soil is resisting, so the soil is pushing back. So there builds up this compression between the anchor and the soil. In this particular case, because of that compression, we call this a passive condition. The passive condition is, if I'm going to draw this, let's say that I have some wall or face. I have the soil behind the wall or face. If I rotate that wall into the soil, or if I move that wall into the soil, it's going to cause the soil to kind of bulge up, maybe something like that. And what ends up happening is if I move it or rotate it enough, it will cause the soil to fill in that manner behind the wall. And what we have happening is we have that soil is trying to move that way, and we have friction along that failure plane going that way. You see how the two arrows are moving basically against one another, towards each other. So this is compression in the soil. When we have that type of compression, we call this, again, the passive condition or the passive loading case. We have another condition where here in the middle, if there's no loading going on at all, we have no induced stresses, we have just the soil all by itself sitting under its geostatic stresses, the vertical and the horizontal, and everything is in equilibrium. We call this an at-rest condition. So the lateral earth pressures that the soil would be feeling in this state are the at-rest lateral earth pressures. Now, if we took the opposite condition, we're going to show this on the right. If we have a retaining wall, you can imagine that this soil behind this retaining wall, it doesn't like being vertical. Soil wants to fall down, basically, and wants to make a cone shape like that. That's what the soil wants to do. The problem is this wall is in the way, so the soil is trying to push the wall over. So if I go back to my diagram, I guess I'm going to have to draw a new one. So there's our wall, there's the soil behind the wall. In this instance, if we were to rotate the wall away from the soil, or if we were to move or translate that wall away from the soil, this soil behind the wall would want to fall down. It would want to form a slope that would look like that. So really, if this wall rotated away, or if the wall translated away, it would cause this failure surface to occur behind the wall. And of course, that failure surface would correspond with this slope that we talked about that the soil would want to make. And along this failure surface, because it's sliding down, we'd have the soil going that way in that failure wedge, and there'd be friction in the opposite direction in this slope. So now the arrows are going away from each other instead of towards each other. So this would be extension or tension in the soil. So what this is actually going to look like when it's all said and done is there's going to be, the soil is going to slump down a little bit behind the wall. There will be a failure surface, and this failure wedge behind the wall will be moving down, and the wall will be holding it up, and all of this soil over here on the right is being held up by its own shear strength. So if we have a condition like this where we have extension or tension in the soil, we call this the active condition. So passive is where we have compression in the soil because the wall is pushing into the soil and the soil is sliding up, it's being pushed into itself. And so because of that compression on that shear plane, that's the passive case. The active case is the opposite. The wall is moving away from the soil, and so the soil under the force of gravity is sliding down, chasing the wall. And so on the failure plane that develops in the soil is pulling apart. That's extension or tension. That's the active case. Now, oftentimes in practice, we compute or get this sigma prime h, that h is for horizontal stress, we compute it as a function of the vertical stress. We know vertical stresses. We've been dealing with them all semester long. These are just the effective vertical stress or the geostatic stress. Or it could be the effective vertical stress plus the induced stress that we apply to the soil, maybe on the ground surface. Anyway, if we know that stress, all we need to do is get this factor K, and we can multiply that K factor by the vertical stress to get our horizontal stress. So this K is what we call a horizontal earth pressure coefficient. And that earth pressure coefficient is going to change depending on what lateral earth pressure case we're dealing with. If we're dealing with the case where the wall is being pushed into the soil and causing the soil to compress against itself, then we call that the passive case. So there's going to be a little p for passive in that case. So that's going to be our passive earth pressure coefficient. If the wall is rotating away or sliding away from the soil such that the soil slides behind the wall following it and it creates extension in the soil along the shear plane, then that's what we call the active case. So you can see there's a little a down there in our subscript. This is the active earth pressure coefficient. And if everything is at rest and nothing is moving relative to each other, then we just put a little naught, a little zero down there to represent the at rest earth pressure coefficient. So each of these earth pressure coefficients is computed differently, and in this lesson and in the next lesson that we'll post probably next week, we'll discuss how you can calculate those. A couple of things though. Let's say that I had let's set up an experiment. So I have my retaining wall. I have my ground surface above and below the retaining wall. And let's say that I had a very special sensor right behind the wall. And that sensor could measure the horizontal pressure that was felt between the soil and the wall. So let's say, and because of that, because we know that the horizontal earth pressure is simply equal to K times the vertical pressure, then we can compute K is simply the ratio of the horizontal stress to the vertical stress. So let's say then that because of this sensor right here, we can track what the earth pressure coefficient is as we slide our wall to the right into the soil or to the left away from the soil. So let's start by taking it away from the soil. So this would again be the active case. So if I slide the wall away from the soil, it's going to cause a failure plane behind the wall to develop. There's going to be opposing forces along that failure plane. Everything will be an extension. So this is going to be the active case. If we were to plot then that K value, what we would see is that K would reduce from the at-rest condition. It would come down, 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 but eventually it would bottom out. It would hit a constant value and it would never change again. It would just remain constant. So at this point right there, that's a failure condition, and we call that the active condition or the active failure condition. It means that we've developed the shear plane in the soil, and the soil basically, that earth pressure coefficient cannot be reduced any more than it already is. So let's go back to our little experiment. Let's change the direction of our loading so that now we're pushing the wall into the soil. So by pushing the wall into the soil, that's going to cause our shear forces along that failure plane to look something like this. So now we're in compression along that plane. And we call this the passive condition. So if we were to plot the behavior of K in this condition, it would increase, but notice that we have to move or get that movement a lot more than we did for the active case. We have to move it a bunch more, but eventually it's going to reach a peak and then it's just going to level off and not increase anymore. That peak is what we call the passive condition or the passive failure condition. At that point, we generate a shear plane in the soil, and the soil is just sliding along that shear plane, and it will not produce any larger earth pressure coefficient than what's already there. So a couple of conclusions we can make from this little make-believe experiment that we did. If I look again at just this plot, think about what we're seeing. In general, for the active condition, Ka is going to vary anywhere between 0.2 to 0.4 of the vertical stress. For the passive condition, it's going to vary anywhere between 3 to 10 times the effective vertical stress. So in other words, our little soil element is feeling way more stress in the horizontal direction than it is in the vertical direction when we induce passive loading in the soil. If we were to measure the at-rest, it's going to be between 0.4 to 0.6, with an average being 0.5. So in other words, under normal circumstances, the horizontal stresses are roughly about half of what the vertical stresses are. which is interesting. Water, because it's hydrostatic, the horizontal stresses are equal to, or a factor of 1, equal to the vertical stresses. But soil is not hydrostatic. The horizontal stresses in at-rest conditions are less than the vertical stresses. So some of the conclusions we could come to from this little hypothetical study: the passive pressure is much larger than the active pressure by orders of magnitude. And that's a good thing. Soil passive pressure is rarely inflicted upon infrastructure unless the soil, under the force of gravity, slides into an infrastructure object and the object has to resist that movement. But for the most part, we rely on passive pressure to give us resistance when we want resistance. So anchors or lateral resistance on foundations, those kinds of things are provided by the passive resistance. So we use passive resistance all the time to keep stuff from tipping over. We also notice that to develop the passive earth pressure coefficient, it requires a lot more movement than it does to develop the active earth pressure coefficient. In fact, if we look down here at some of these numbers that Professor Kyle Rollins developed for us, we can see that studies have shown if I'm tilting the wall away, so this case represents the active condition behind the soil. Look at how much I have to tilt the wall away. That's this delta LA. Delta LA is given in terms of a ratio relative to the height of the wall. If I have a loose sand, I just have to move that wall 1/500th of the height of the wall to develop the active condition. That is not very much. That's like 0.2% that I need to move the wall. But as opposed to the passive condition, for a loose sand, I need to move it 1/100th of the wall into the soil. This is the passive condition. So rotating that wall into the soil, it needs to be about 1% of the height of the wall. And it varies for the type of sand. So if I have a dense sand, for the active condition, it's even less than that. It's now like 0.1%, as opposed to here, it's also 0.5% maybe. So you can see that it takes less strain to develop the active condition than it does to develop the passive condition. Finally, because we talked about how these stresses level out, they don't change once you reach them, we can say then that the active earth pressure coefficient and the passive earth pressure coefficient both represent terminal failure conditions. The soil is a failed, and you're not going to change the resistance anymore once that failure plane develops. So let's teach you how we might compute some different earth pressure coefficients. The easy one that we'll learn right now is the at-rest earth coefficient. Most geotechnical engineers use this relationship to approximate it for normally consolidated soils. That's both clays and sands. We approximate it as a function of the friction angle. So if we can get the friction angle, and notice it's the drained friction angle, not the undrained friction angle. If we get that drained friction angle, we'll see that generally K0 ranges from 0.4 to 0.6. If the soil is over-consolidated, then we just have to add this factor in here to adjust our approximated over-consolidated soil. So we notice that with that OCR factor in there, it's going to increase the the lateral earth pressure coefficient. So why would lateral earth pressure coefficient increase for over-consolidated soil? You might pause and just think about that for a minute. The answer to why the lateral earth pressure will increase with over-consolidated soil is generally because the horizontal stresses tend to get locked in a lot more than the vertical stresses do. Vertical stresses will come and go, and the soil can respond relatively well to those. But if you make changes in the horizontal stress, just because of the nature of soil particles, those stresses get locked in. And so they don't respond as well when you take stresses away. So one of the most common theories that engineers use today is what's called the Rankine method, or the Rankine theory, for computing active, so that's our Ka, and passive, Kp, earth pressure coefficients in cohesionless soil. So these are going to be sands and gravels. This theory was developed in the late 1800s, but we still use it today. So it is very old, but it's still very good and valid for a lot of conditions. This theory, by the way, makes some critical assumptions. It neglects friction between the wall and the soil. In other words, according to this method, the only friction that exists in the system is between the soil particles themselves. Now, we know this isn't true in real life, but it's an assumption we make to simplify the problem. So here we go. We're back to our little experiment again. Let's imagine now, here's a little soil element that I can adjust these horizontal loads. So imagine if I adjust the load and I reduce these horizontal loads. Here's my Mohr circle for the initial loads that are applied, where this is sigma 3 and that's sigma 1. Now as we reduce these loads, that's sigma 3, that's sigma 1, as we reduce these loads, that's going to cause this sigma 3 to move to the left, to the point where, see if I can get my animations to work, the circle is going to get bigger, and eventually it's going to hit the Mohr Coulomb failure envelope and cause a failure in the soil, where we're going to have extensional failure occurring. Now, if we look at the Mohr circle, sigma 1, which is defined as the larger of the two principal stresses, is still the vertical stress. That never changed. The horizontal stress was reduced, and so that's sigma 3. So if we keep reducing the lateral load, it will eventually hits the Mohr Coulomb failure envelope, and we develop a failure plane. At the moment it touches the failure envelope, that's when we reach the active case. That's when Ka is fully developed. Now, let's reset our little experiment here, and let's increase the lateral earth pressures. So if we increase them, our initial stress here is going to move to the right, and it's going to keep moving. It's going to pass sigma 1 and eventually come over here and keep going to the point now where now it becomes sigma 1 because it's the larger of the horizontal and vertical loads on the soil. Remember, sigma 1 has nothing to do with whether it's vertical or horizontal. It's always just the larger of the two. So now the horizontal stress is the larger stress, and so now it becomes sigma 1. And the vertical stress becomes sigma 3. And eventually we'll hit the failure envelope again. And if we hit that failure envelope, we now fail the soil in compression. This is the passive condition. And this is when we've developed K sub P. So this was Rankine's theory that's tied the Mohr Coulomb theory in with what he was observing in lateral earth pressures. Now, if we take this common relationship, which is just based off the geometry and trigonometry of the Mohr Coulomb circles and the failure envelope, we can simplify for Ka and Kp using these relationships down here. So Ka is simply, remember, for the active case, the horizontal stress equals sigma 3, and the vertical stress equals sigma 1. And remember, K is the ratio of horizontal stress divided by vertical stress. So if that's the case, we have sigma 3 divided by sigma 1. And if we can plug in this relationship here, and if we do so, then we get this famous equation. This is the Rankine equation for computing the active earth pressure coefficient. And the failure orientation that we would get if we drew the failure plane through the pole equals this angle right here. For the passive condition, by the way, the horizontal stress becomes the larger stress, so that becomes sigma 1. The vertical stress becomes the smaller stress, so that becomes sigma 3. And because K equals the horizontal stress divided by the vertical stress, we get sigma 1 divided by sigma 3. Simplifying, we get this equation for our passive earth pressure coefficient using the Rankine method. Folks, the only difference between these two equations, passive has a plus, active has a minus. That's it. Other than that, they're the same equation. Also, in terms of our failure orientation, if we were to draw the plane of that failure surface through the pole, for the passive case, it's a minus. For the active case, it's a plus. And again, all of this is just based off geometry from the Moore circle. So, if we look at an actual retaining wall system, here's our retaining wall. This is what we would call a cantilever wall, because you have this section out here that cantilevers underneath the soil, and the weight of the soil presses down and helps keep the wall here upright. So we call this a cantilever wall. For any retaining wall problem, there's always going to be a combination of active and passive happening at the same time. So for instance, over here I have the ground surface in front of the wall, and back here I have the ground surface behind the wall. The ground surface behind the wall is trying to fall down. The ground surface in front of the wall is trying to keep the wall up. So we have this combination of active forces acting behind the wall, where we have this triangular pressure distribution that increases with depth, and that at any depth, that stress acting against the retaining wall is simply equal to, remember, this is just the vertical stress times our earth pressure coefficient. And if we want to find the equivalent force from the active condition, we just have to sum the area in this triangle, because that summation of the area is like the integration of the stress. It gives us the force. So the area of that triangle is simply equal to this equation, 1/2 gamma h times K times another h, or the height of the wall. So that's how we get the force. Now what about the soil that's resisting, or that's in front of the retaining wall? Well, that's passive force. So that's simply going to be our vertical stress at whatever depth we're interested in times the passive earth pressure coefficient. It's not active because the wall is pushing, it's being pushed by this soil behind it. So the wall is pushing into this soil over here. So the soil is being put into compression in front of the wall. Behind the wall, it's in extension. So now we have this passive resistance that's helping keep the wall in place or hold the wall up. If we want to compute the force, equivalent force that's helping support the wall, same idea. We just have to get the area of this pressure distribution. That area equals the force from the pressure distribution per unit width into the page, and so that would be then our 1/2 gamma H2 squared times our passive earth pressure coefficient. So any real retaining wall problem is going to have a combination of active and passive pressures working in conjunction with one another. So here's the deal. I'm guessing if you're in the United States that at some point you're going to want to take the Fundamental of Engineering exam, or the FE exam. Every civil engineering practitioner wants to take this exam and pass it so they can eventually get their professional license. I can guarantee you that you are going to encounter a lateral earth pressure retaining wall problem on the FE exam. They're almost on every single exam. And students freak out when they see these problems because they go, oh, they just panic. They don't know what to do. So I have boiled it down to 7 dummy-proof steps that if you just walk through these 7 steps that I've listed right here, you can solve any lateral earth pressure problem. A simple problem or a hard problem. And a hard problem might be one where, say you have an induced stress on top of the wall, and you might have water behind the wall that the wall needs to support as well as the soil. You also might have multiple soil layers behind the wall. All of those little scenarios make the problem more complex, but it doesn't change these 7 steps. If you can follow these 7 steps, you're going to be in good shape. So let's go ahead and just solve a problem. And I could solve a simple problem because I know that you guys are being introduced to this for the very first time. And that might be a good idea. But I'm just going to jump to the most difficult problem that you are likely to see on the FE exam. And I'm going to show you that even with the most difficult problem, we can solve it using these 7 steps. So let's go ahead and jump right in. Step number 1, you're going to recall, is drawing the problem. So here we are. We're going to draw and label the problem. So here's a problem that is given to us out of our textbook. It's a 6-meter high retaining wall that has 2 types of soil behind it. We have a loose sand that's 4 meters thick, and we have a dense sand that's going to be 2 meters thick. It's obviously not to scale. It's a frictionless retaining wall. If you see the term frictionless, that right off the bat should be a trigger for you to know that we're doing a Rankine method. We'll talk about other methods in the next lecture where friction is accounted for, but a frictionless wall is going to be Rankine. We have a surcharge on top of the wall that's causing additional induced stresses for our soil elements behind the retaining wall. So this is what our problem looks like. Oh, and I neglected to tell you we have groundwater that is also going to be supported behind the retaining wall. So this retaining wall is being asked to hold up a lot of stuff. And what we want to do is we want to find the equivalent horizontal force acting on the wall. So that's going to be this P that's acting on the wall. Not the pressure distribution, but the equivalent force P. Okay, well that's step 1. I gave it to you. Now step 2, we have to decide whether or not this problem is active, passive, or at rest. Now I know that this takes a little bit of practice to conceptually get or to understand, but I want you to think about this. In this particular problem, is the wall rotating away from the soil, or is it rotating towards the soil? In order for the wall to be rotating towards the soil, there has to be an actual force or mechanism that's causing it to rotate. If the wall itself is just sitting there, then the only direction it's going to go is rotate outwards. And if it rotates outwards far enough, it's going to develop a shear plane behind it. In fact, here's something that's interesting, a little side note. Geotechnical engineers always design retaining walls, well, almost always, to be active. And the reason they do this is if we can rotate the wall, that 0.2% that's necessary to develop the active condition, then the wall only needs to hold up this little wedge of soil. All of this stuff over here, all of that soil is held up by itself under the soil's own shear strength. So if we can develop an active condition, we just need to hold up this little wedge right here. And so it's a lot more economical to do that. So if you see a retaining wall problem, it's almost always going to be active. In this particular case, it's active because the soil is developing extension behind the wall. The soil is trying to push the wall over, the wall's yielding away, and it's causing the soil behind it to chase it and develop that extension in the soil. So we have the active condition. We're going to be using the Ka term in this problem. Now, unless I specify or tell you that there's some force or strut or something that's pushing the wall into the soil, it's always going to be the active case. If there's a strut or a force pushing the wall into the soil, then it would be the passive case. But we don't have that kind of force or strut in this particular problem. Okay, so that's step 2. We've determined that it's the active condition. So step 3, we need to compute our earth pressure coefficient. And for this case, it's going to be the active earth pressure coefficient because we have the active case. So remember that according to Rankine, the active earth pressure coefficient is simply the tangent squared of 45 degrees minus phi divided by 2. So we have 2 different types of soils. We have one friction angle that's 32 degrees, and we have another one that's 38 degrees. So we can apply that equation of tangent squared of 45 minus phi over 2 for the top soil, and we get 0.31. For the bottom soil, we put in the different friction angle, and that results in 0.24 for our soil down there. That's simple. Step 3. So we're like halfway done already, guys. So far, not too bad, right? Step number 4. And this is the step where probably the majority of people make mistakes, but you shouldn't, because step number 4 is simply computing the vertical effective stress behind the wall. This is something that you guys have been doing for a long time already. You guys have already been computing geostatic stresses. So what I want you to imagine is, imagine a plot overlaid on top of your wall where this axis here is depth and this axis here is effective stress, vertical effective stress. So I would expect at the top of my wall, because I'm right at the ground surface, to have 0 effective stress. And I would expect my stress to increase linearly at a rate of the unit weight of the soil, gamma. Gamma moist if it's moist, or once we get below the water table, it's going to increase at the rate of gamma buoyant. That's the saturated unit weight minus the unit weight of water. So let's go ahead and calculate. What I like to do is pick key points in my soil profile. Key points are points where the soil layering changes. So let's identify all the places where the soil layers change. We have the top of the soil. We have this transition point between the two soil layers, and of course we have the bottom of the soil profile. So we have three key points in our soil profile. So we know also that this surcharge, it's an infinite surcharge, because we're assuming that this thing goes infinitely in that direction. So because of that, we're going to treat our induced stress as uniform with depth. So this stress that I just plotted right here, this stress right here, this is our increase in stress, or that's equal to our Q. And then we know that there's going to be a stress from the upper soil, and then of course a stress from the lower soil. So let's go ahead and compute these stresses at these three key points. At the top key point, where our depth is 0, we know that there's no weight from the soil, but we do have weight from the surcharge. So because of that, our vertical effective stress right at the ground surface is 15 kips, or 15 kilopascals, because of the surcharge. Now, as I increase with depth, as you'll recall, our stress is going to increase at a rate of the moist unit weight. So when I get to a depth of 4 meters, my effective vertical stress is going to equal the surcharge plus the effective stress, which is just the moist unit weight times the thickness of the soil. So moist unit weight for the upper soil is 16 kilonewtons per cubic meter. That was given. And the thickness of the soil is 4 meters. That was given as well. Again, the surcharge remains the same at 15 kPa. So doing that at this hinge point right here in the middle, the vertical stress at that point is 79 kPa. At our final hinge point at the bottom of the wall, that's at a depth of 6 meters. The vertical stress is going to equal the stress from 4 meters plus this additional stress from the bottom layer of soil. So remember, this saturated unit weight minus the unit weight of water, that's the buoyant unit weight of the soil. So all we have to do is add that unit weight times this thickness of the lower soil, which we said was 2 meters. That's this guy right there. So the total height of 6 meters minus the height from the top of 4 meters, that leaves us 2 meters. So if we plug in all those numbers, this is the value that we get for our vertical stress at the bottom of the wall. So hopefully, you guys, let me erase all my marks here just so we get a little cleaner picture and you can see what's going on. You should be able to compute vertical effective stresses at this point in soil mechanics. So if you're struggling with this, stop and take the time you need to understand what's going on here. If you're struggling to understand it and you need some help, come see me or come see a TA so that you can get these vertical stresses. This step number 4, is the number 1 key step in solving lateral earth pressure problems. Okay, So let's move on now to step 5. That was the hardest part. Step 5 is a piece of cake. Now that we have the stresses at the key points of the wall, wherever we had a change in soil, or we were at the top or the bottom of our wall, all we need to do now is compute the horizontal stress, and that's simply going to equal the earth pressure coefficient times the vertical stress. So we just have to multiply the vertical stress that we computed by the corresponding active earth pressure coefficient. So at a depth of 0, you'll recall that the vertical stress was 15 kPa from the surcharge. The active earth pressure coefficient was 0.31. So by multiplying them, I get 4.7 kPa. Now, at the middle, we have something interesting because we have the active earth pressure coefficient for the upper layer is 0.31, but you'll recall that for the lower layer, right at that same boundary, it changes, I think, to 0.24. And that happens right at the same point. So what's going to happen is we're going to see a very sharp transition in the horizontal stress at that depth. So let's think of it this way. At a depth of almost right to the boundary, say 3.99999 meters, so we're still just barely in this upper soil layer. We're going to be in that upper soil layer, so my active earth pressure coefficient will correspond to the upper layer's earth pressure coefficient of 0.31. So we're going to just multiply the vertical stress at that depth times the earth pressure coefficient of 0.31, and that gives us a stress of 24.5 kPa for our horizontal stress. Now at a depth of 4.00001, now we're just barely into the second soil layer, so our active earth pressure coefficient has now changed to the 0.24. But we're going to say it's about the same vertical effective stress. So all I need to do is multiply that same vertical effective stress by the active earth pressure coefficient from the lower layer. And by doing that, I get 19 kPa. So that's why we get this sudden shift in our stress profile. And then at our bottom depth, at a depth of 6 meters, because we're definitely now in the second soil layer, we just have to take the stress that we computed from step 4 and multiply it by the active earth pressure coefficient we computed from step 3. And by doing that, we get 23.4 kPa. Wow, so we just computed horizontal stresses. Awesome. Are we done yet? Well, we would be if we didn't have any water behind the wall, but we have water behind the wall. So that water, this water here, is applying its own hydrostatic stresses on the wall, and we have to account for that. So that's step number 6. So here are the hydrostatic stresses being applied to the wall from the water that's being held behind the wall. And this is just like from your fluids class. At a depth of 4 meters, the stress from the water is equal to 0. But at a depth of 6 meters down at the bottom of the wall, because we have 2 meters of water that we have to account for, we just have to take the unit weight of water and multiply it by the depth of water, which is 2 meters. And that gives us 19.6 kPa for our horizontal stress from our water at the bottom of the wall. Cool. So check this out now, you guys. What we've essentially done is we've developed this big stress profile that's acting on our wall. And this stress profile is what we need then to sum up and integrate basically to get our equivalent force P that's acting on the wall from the soil and from the water. So to do that, we just have to compute the area of those stress distributions. So now we're just doing geometry. So take this big stress distribution. Here, let me outline it. Take this big stress distribution and just break it up into shapes. And that's all I did here. I just broke it up into shapes where I know the dimensions. And I know the values of the stresses. And all I have to do then is compute the area of these shapes and sum them up. So from the first shape, I just made a giant rectangle. And that's the size of this rectangle here was 4.7 kPa. So, and it's 6 meters high. So by multiplying 6 meters by 4.7 kPa, I get 28.2 kilonewtons of force per meter depth into the page. Shape number 2, same thing. Now it's a triangle, so I'm just using the geometry of the area of a triangle to compute these things. Shape number 3 is the area of this rectangle here. So go ahead and you can write these equations down for the different shapes. But what I want you to do is go back through the numbers we calculated and see where these stresses, 19, 24.5, 4.7, 4.7, see where those stresses come from so that you understand what we're doing. The final shapes, shape number 4, that's the triangle, and shape number 5, the triangle from the water. So once I have the areas for all these 5 different shapes I created, just sum them together. And by summing those, that gives us the equivalent force acting on the wall. Now, if I wanted to find the location of this, I would just take the equivalent force from each one of these shapes. We're on a triangle, it's working 1/3 the way up the height of the triangle, and for a rectangle it's at 1/2 the height of the rectangle. And I would sum the moments about the bottom of the wall, where the sum of the moments have to equal 0. And I would compute then, once I have my equivalent force, PA, I would then compute the location or the moment arm of PA such that I can compute the sum of the moments to equal 0, given all of the incremental forces acting on the wall. So I'm not going to walk through that process. It's something that you should already be familiar with, hopefully from statics, but hopefully you see the process, how that works. So that's it, folks. I mean, we just solved the most challenging lateral earth pressure problem you're going to see on the FE exam. And I like these types of problems, so expect to see these on the final exam as well. So I encourage you to get really comfortable with this example problem and with your homework problems so that you're prepared and ready for the final exam. So I know this was a long lecture, but I appreciate your patience through it, and I'll look forward to seeing you in the next one. Talk to you later.